Okay, we continue with Chiara. Probably today we'll hear something about entropy localization. So
Yes.
looking forward to it.
Okay, very good. Okay, I hope that this is readable. I've written something on the blackboard. So first of all, so what we are gonna do today is that I'm gonna show like how to match the black hole entropy and in particular the black hole Auger action to the partition function of the dual field theory. This for ADS black holes, it means that the partition function to which we are going to match is the partition function of a BGM theory, which is the three-dimensional dual conformal field theory that lives on the boundary. I will teach you a bit the basics of localization. I'm not, as I was mentioning, I will deal mostly with the gravitational side of the story, but I'm going to just tell you at least a bit how the computation works in the dual field theory. And then I'm going to analyze two examples of entropy matching. One for static black holes here, which are these ones that I explained the other time. And then I'm going to deal with another branch of black holes, which are the rotating supersymmetry black holes. So I'll first explain some generalities about these black holes, and then I will tell you how their entropy can be rewritten in terms of an entropy function, which is something like that comes out very handy, because indeed the fact that the entropy function assumes a very particular easy form, like triggered the match with other kind of field theory like quantities, which are indeed like slightly different than this one, but they are still indices and they are called the superconformal indices. So okay, since I was a bit late last time, I just want to recap the main features of the static solution, and then also I'm going to tell you a bit more about some generalization that one can do before delving into the computation of the microstates. So first of all, as I was mentioning, so we had two different kind of black hole solutions, right? Like from the exercise that I gave you about the Killing spinner, we analyzed just one because that's the one that, when you add scalars, can have an event horizon. So the solution that we are going to deal with in these classes will be versions of the magnetically charged, so-called twisted solution. So that preserves supersymmetry via the topological twist, meaning that in the supersymmetry variation, we cancel some components of the spin connection with a gauge field, with a magnetic gauge field. So our solution in the easiest example is a purely electric solution. The scalar field, since the solution is static, the scalar field is static and spherically symmetric. The scalar fields depend only on the radial coordinate. Moreover, we have that supersymmetry. Supersymmetry indeed picks out a particular value for the Dirac quantization condition, meaning that the sum of the magnetic charges like contracted with these quantities here, which are the Fay-Heliopoulos parameters. So these quantities psi determines your theory. They appear, for instance, in the scalar potential. And so indeed, if you contract this, this is exactly like the charge of the fermions in your theory. This one, the G lambda, are the charges of the fermion, which contracted with the magnetic charges needs to give an integer for the Dirac quantization condition, and supersymmetry picks out the value 1. So this solution here, they can have a horizon when the scalars are switched on, because the scalars are responsible for this parameter c to be negative, and can have a different horizon, can have spherical, planar, or hyperbolic horizon. And this can be seen as a flow from ADS4. So the solution asymptotically is approaches ADS4 spacetime, because indeed the scalar potential is negative, and it flows to a geometry which is ADS2 times sigma g, where sigma g can be a two-sphere, can be like just R2 or a toroidal horizon, or a higher genus Riemann surface. The higher genus Riemann surface is obtained by compactifying the hyperbolic two-dimensional hyperbolic space. So at ADS4, the potential is extremized, but it means also that this quantity here, which is called the gauging potential, which is defined in this way, is also extremized. In all our cases, we don't consider this part because we don't consider magnetic gauging. We don't consider like Fay-Heliopoulos with upper indices. So we just consider our theory will be just characterized by this sort of gauging. So this quantity here is extremized at the ADS4, while at the ADS2 near horizon, on the near horizon geometry, which is ADS2 times sigma g, the quantity that needs to be extremized is a particular combination of this Z, which is the cold central charge, and again, the gauging potential. So, okay, this is for what concerns supersymmetric solution with a twist. Let me just mention, just briefly, a couple more things about these solutions. So these solutions can also be generalized to higher dimensions. And in this case, in particular, we can have solutions which, again, preserve supersymmetry, in general, 1/4 of supersymmetry, if you consider n equals to 5-dimensional gauge supergravity. And there can be solutions that are ADS5. So these solutions go from ADS5 to an ADS3 times sigma d near isogeometry. So these are the so-called black strings. Black strings in five dimensions. And the matching is obtained in a slightly different way. So in this case, the fact that you have an ADS3 near isogeometry is symptomatic that your theory flows to a CFT2. So the matching will be just like computing, will be obtained by computing the central charge of the two-dimensional field theory coming from the reduction of n equals 4 superior means, for instance, and matched via the Brown and No formula to the ADS3 radius that you get in the supergravity solution. I'm not going to deal with that, but just to say that there are generalizations of this to higher dimensions, and generalization also to other kind of dimensions, for instance, solutions which are in ADS6 that flow to ADS2 times, for instance, sigma G1 times sigma G2, and so on and so forth. I'm not going to deal with those, but just remember that there are similar solutions that indeed preserve supersymmetry, again, by turning on some component of the magnetic gauge, some magnetic component of the gauge field in this direction. Moreover, we can also just go beyond SUSY, given that one has this solution here. These solutions are fully analytic solution to the Einstein's equation. They have been found by solving the Killing-Spinor equation. However, once you know that solution there, it's easy to find different solution, even more complicated solution, just by pretty much modifying some of the work factors that are present in these geometries. For instance, if we want to go beyond SUSY, we can find so supersymmetric solution also, given that you have an ADS2 near isogeometry, is also at 0 temperature. I hope you recall that indeed when you have 0 temperature, you have an ADS2 throat, let's say. If you want to deform it out of extremality, you just need to take the metric as it is there, but modify the GTT and the GRR component in this way. So this goes at GTT, and this is also the factor that goes like at the denominator of GRR. This allows for the fact that your solution will have then two horizons which are not coincident, but it will have to, it will be a separation between the two horizons, so the solution will have temperature. One of the very remarkable fact about the supergravity in general, the supergravity theories in these sort of models, is that you just need to modify this work factor in this way. You leave the scalar fields unchanged, and also your ansatz for the magnetic fields. Of course, you need to find some suitable form for these parameters that they are here, but in general, just with a simple modification, you can find an analytic solution of the Einstein's equation. Moreover, just as a last remark, you can also find solutions at 0 temperature equals 0, but non-BPS. So for some of you, maybe these are the analog in gauge supergravity of the almost BPS solution. Maybe some of you don't need, but basically they are found by rewriting the supergravity action in terms of squares. So you have to, via suitable ansatz, you will manage. So this happened for the BPS solution, meaning that you can, given a suitable ansatz for your solution, you can rewrite the supergravity action in terms of a sum of squares, and each factor of inside the square is a BPS equation. It turns out, and indeed, when you compute the equations of motion, by putting all the factors inside the squares to 0 independently, you get components of your Killing-Spinor equation. So it turns out that you can do this. You can slightly modify, like so you can rewrite your action in such a way that this equation here that fall inside the squares are not precisely the BPS equation, but they differ by some switch of signs. And this indeed gives you a solution that breaks all the supersymmetries, but still it is at 0 temperature. So this is just an aside to see that once you get this solution, it's very easy to get new ones, analytic, that solve the full system of Einstein's equation. And in this case, for instance, you can also study the thermodynamics. Thermodynamics like we did in the first lecture, but for now, we don't do that, but if you're interested more, I can give you more details about this. So, okay, this is just as an aside. Now we are ready. Now we are just ready to go back to our supersymmetric configurations. So indeed, once we want to match the entropy for this sort of configuration there. It is handy, however, though it was not found first in history, to work with some simpler solution, because if you remember, there were some hyperbolic solutions which have a well-defined horizon while having zero scalars, and these are the ones that we'll take into consideration. So we're going to start with the minimal solutions. Which are also called universal, because they sit in every Sasaki-Einstein 7 truncation. So this can be obtained by, let's say, M theory on Sasaki-Einstein 7. So we have already seen these solutions here. So I'm just gonna write them like this. So this is in the end, the free strength is only this. Okay. So for SUSY configurations, we have this. We have that U equals GR. 1 over 2 GR. So it's really easy to see that the horizon, like the solution, has two coincident horizons, R plus equals R minus equals 1 over square root of 2G. Okay, so this solution here has a hyperbolic horizon, and it has really a horizon because the warp factor indeed goes to 0 for a positive value of the radius. This is something that I've already mentioned last time. Is one of the subset of the solutions and can be retrieved by this solution by setting the scalars to constant. So this will be our first example, the first example that we're going to analyze. So first of all, we compactify the Riemann surface in order to work with something like with a compact horizon. So the black hole entropy. So if you have to use the Gauss-Bonnet theorem, that pretty much just shows that, so that relates the volume of this compact manifold to its genus, and it just boils down to this. Therefore, we can immediately get the value of the entropy. So this is the 4-dimensional Newton constant. So this is the value of their entropy. This is something that we would like to retrieve via computation on the dual field theory. However, so from the dual field theory via localization, we get a lot of like quantities which are the supersymmetric partition functions. So partition function is in general related to the on-shell action of these solutions, but while here we have only the entropy. So in what I want to show in the next few passages is that indeed there is a relation between, like in this particular limit that you have in which the black hole is supersymmetric, there is a relation between the black hole entropy and the on-shell action of the solution once this is suitably renormalized. So indeed, for all the anti-de Sitter configurations, if you compute the on-shell action naively, you get divergences. So there are divergent terms when you plug a solution inside the on-shell action. So you have to adopt a suitable renormalization procedure, and people have developed that. It goes under the name of holographic normalization. And that's what you need to do in order to compute this thermodynamic potential, then you can exactly match to the partition function in the dual field theory. So this is what we're gonna do next. So I hope you're familiar like with the notion of maybe on-shell action, or just like I guess the thermodynamic potential. Okay, so basically what you need to do to compute the on-shell action is that we are gonna take yeah.
M should be the horizon, right? Is the volume of the horizon, which is the Riemann surface of genus G.
Exactly, yes.
But in this case, we wrote the metric of the hyperbolic two-plane, in this case, and as the genus is zero, I mean I cannot see the genus.
No, so basically, this you get it because so the volume of two-dimensional hyperbolic plane is actually infinite. It's a non-compact manifold, exactly. Like it goes like this. So what you need to do is that you need to compactify this surface and get a higher genus Riemann surface. Imagine in the most simple case, instead of having a hyperbolic plane, imagine having just R2. You can compactify it by making it into a torus. So that's exactly the same things that you will get with a higher genus Riemann surface, like from hyperbolic space to a higher genus Riemann surface.
I see. So it's the compactified Riemann surface that I get out of the hyperbolic two-plane.
Exactly.
Okay.
So you use the Gauss-Bonnet theorem that relates the volume of this surface to the genus in order to have somehow normalize your area.
And genus should be bigger than one, strictly bigger than one?
For now, yes. So this exactly. G should be bigger than 1. You can also do it. I mean, strictly speaking, the matching and so on is done for G bigger than 1. The case G equals 1, you have to treat it separately.
Okay. Thanks.
Okay, so as I was mentioning, what we need to do things more, let's say, to do things very like precisely or more correctly is that we have to match the partition function of the dual field theory with the on-shell action of these black holes. And in general, we have to resort to holographic normalization. So the on-shell, let me see just a moment, let me write down. So the action for all these black holes is this one. We have seen it many times by now. So we have seen it, for instance, many times, but also, for instance, we have computed the on-shell action or the difference between on-shell actions when we dealt with the Hawking page factorization. I don't know if you remember, we had to plug everything in, take the difference, and making sure that the boundary conditions at infinity between ADS and the black hole were the same. And then we got the factorization. So basically, the action is this one. The point is that, so in order to we will plug in this solution here, and then we will need to perform the integration between, for instance, between R plus. So the integration goes on the H2 or on the sigma G, let's say. From R goes to R plus to a cutoff, which we said large cutoff, large radial coordinate, and then we're gonna add some counter terms, so then all the terms divergent here will just be normalized away. But the problem arises when, this is the Euclidean on-shell action, so we have to first weak rotate our solution into Euclidean signature, and then we have to integrate our solution like on the period of the time circle, Euclidean time circle. The point is that if you remember, this like the period of the Euclidean time circle is inversely proportional to the surface gravity. So for all these black holes here, these black holes are supersymmetric and they are also zero. So in these cases, we have a bit of a problem because we will have a divergence there when we try to integrate over the time direction.
So can I ask a stupid question? What is the proof that a SUSY black hole has to be a zero temperature, assuming everything is smooth?
Well, in a sense, you don't want, let's say, well, we have seen that for sure some configurations, on some configuration, for instance, they are naked singularities, so you cannot even define a temperature.
Yeah, but is it a general fact that in any black hole solution in Lorentzian signature that's smooth, has a horizon, that if it's BPS, it has to be zero temperature?
I think so. Maybe there are some solutions, I don't know, these fuzzball solutions that people study, but I know that with the well-known, like black holes, like I think it is a fact that you need to have zero temperature. In general, supersymmetry, requires the same boundary condition between fermions and bosons, and if you have non-zero temperature, you cannot do that because fermions are antiperiodic, and then
pick up some mass if you have some non-zero temperature, I think, if I'm not mistaken, and then you have a mismatch between bosons and fermions acquiring mass or something, depending on the boundary condition you put on the thermal circle, but not around the details completely.
yes, for sure. I mean, I think that so there exist some solutions like fuzzball solutions that I guess that they do not, strictly speaking, have a horizon. So yes, for that I also don't know how would you define the temperature. Maybe I don't know. Maybe.
Yeah,
David?
I don't know any examples
But,
of supersymmetric black hole to which one can associate to non-zero.
I was just wondering if there's a theorem, or is it just like we've explored lots of examples and there's no such?
It's a good question. I'm not so sure. I think there should be arguments, at least in specific contexts. You can often associate some kind of left moving temperature in a dual field theory, but this is still the case that the physical temperature in the ball will be zero.
You know that, for instance, in Euclidean signature, situation will be very different because you can have solutions that cap off smoothly that are more similar to black holes with temperature, but then you have some problem rotating them back into Lorentzian signature. So yes. So for this sort of configurations, we have that the Lorentzian solution has temperature equals zero. However, if you have to rotate it, like weak rotate, and then integrate to get the on-shell action, you will have a divergence. So what you need to do, however, you can also, in these cases, you also have like particular choice of mass. For instance, if you remember here, the mass of the solution was zero, and the magnetic charge, I don't know how do I call it at that time, but it was like minus 1. So you can hope that at least in the limit, so what you need to resort to is to take a limit, go a bit above extremality, so consider the solution which is non-extrema. So you compute the on-shell action for your u factor, which is the square root of g squared r squared minus 1 plus 2m over r plus q squared over r squared. And then you take a very careful limit, t equal that for which m goes to 0, and then this will be p goes to 1 over g. You'll see that the solution really, like, you can take a limit which is very well, well defined, and the divergence that comes from this part here exactly cancelled with some other terms inside the on-shell action. So, and also you have further terms that come from holography normalization. So I'm going to write them down. So in order to normalize the action, so you have to first plug in. So first you plug in the solution inside here, and you impose a cutoff. Okay, here I call it R. Let's call it R0. So R0 is big, let's say, and not to be confused with this R. This is a Ricci scalar. And then you add the counterterm. These counterterms are dictated by techniques of holographic normalization. And they are unambiguous in terms like when you have solutions without scalars, these terms are unambiguously found, let's say. In case of scalars, some of the boundary terms will really depend on the boundary condition that you, so by means of this boundary term, you dictate the boundary conditions of the scalars. But at least in this case, everything is well defined and unambiguous. Like there is no choice, there is only one choice of counterterms, which is this one. And it turns out then, that, let me see, so the temperature of the solution also is this. This is the temperature. This is equal also to 1 over beta. So if you compute, after all, everything, you have that Euclidean action is this. So now, this is completely general. So it is for a configuration which has beta, which in particular is this, of this form here. And only this, you know that beta is infinite, but you have some, let's say, conspiracy between all these terms in such a way that the limit is finite. So if you take the extremal limit, which means that r plus goes to 1 over 2, square root of 2g, you get exactly that the on-shell action that I call I extremal equal this one. So you go really, really close to the, taking the limit for the extremal solution. You have to start, though, from this particular configuration, which is fully, fully generic. In order to avoid, to see that the divergence is cancelled, then you have to take the limit to the extremal configuration, and you have that exactly the extremal on-shell action is equal to minus the black hole entropy. And this justifies the fact that indeed you can associate, you can match minus the black hole entropy with the logarithm of with minus the logarithm of the partition function computed on the dual field theory via the on-shell action. So in a way, for this kind of black hole, computing the entropy, so you bypass computing the on-shell action just by computing the entropy, and then you match the entropy directly with the partition function on the dual field theory. Okay, so now I'm going to explain you just a bit how the localization procedure works. First of all, I think that all of you, of course, all of you are familiar with the ADS-CFT correspondence, but just to give an idea, all these solutions, I will deal the most, let's say, the simplest case in which we deal with ABGM. So how to find, so this as black hole we need to associate to the partition function of the dual field theory. And the dual field theory will be of the form of, will be ABGM. So ABGM is a three-dimensional superconformal Chern-Simons theory with two copies of Chern-Simons with groups UN, level k and set k and minus k for chiral multiplets in the bifundamental and also there is a superpotential. Superpotential that couples all these fields. It's not quite, I mean, it's not, you're not going to do the computation like explicitly on this, but this is just the matter content of your theory. It's a theory that arises on, like, it's a theory of M2 branes probing a C8 or mod ZK. And this is dual to M theory on ADS4 mod ZK with nk units of flux, or let's say 4-form flux on ADS4, or equivalently on type 2A superstring theory on ADS4 times, ADS4 times, S7 mod ZK, ADS4 times CP3.
Flux shouldn't be really through the compact, so isn't ADS4?
Yeah, this one is like, yeah, it is on ADS4 flux. There is, I mean, for this one, there is also k units of flux on CP1 circling CP3. Depends on you how you deal with that. Okay, this is just some particular specification of the theory that we're going to deal with. You remember that probably like from your, I mean, Chern-Simons couplings are like trace of A wedge delay. There are some complicated like Chern-Simons theories with supersymmetry. So for instance, for k equals 1 and 2, you have like n equals 8 supersymmetry, so maxima. Susie, for the other values of k, you have instead n equals 6. So this is the theory that people need to work with in order to find, like, these are the theories which are dual to our setup, which I recall you is n equals 2 gauge supergravity, which arises as a truncation of n equals 8, which is maximal supergravity in 4 dimensions. So it's SO8 gauge supergravity, which then admits ADS4 vacuum, which is dual to that setup. So, okay, we're going to work with that theory there to give you a bit of specification, and we're going to use techniques of supersymmetric localization. So now I'm going to briefly explain how localization works. Fortunately, we will not have time to go through the computation of the partition function, but I'll give you the result. So localization in general is made, so it's made in such a way that it reduces an infinite dimensional integral to a finite dimensional one. for instance, if you want more details, I will refer you to the lectures on localization by Marcos Marigna. Which also deals a lot of, like explains also a lot of things related to localization on a BGM, let's say. So for this case, we consider an action and with some sets of fields collectively denoted by phi, and this action we impose that has like a symmetry, which is generated by a Grassmann odd operator. Such that this operator squares on another operator, which is another, let's say, symmetry. This needs to be a symmetry, which is a Grassmann even symmetry. So, for instance, Lorentz transformation. You can already see that this is a fermionic symmetry, will be related to supersymmetry, of course. So now consider then the following. So consider deforming the partition function, the perturbed we consider a one-parameter deformation of the partition function, which is this. Where V is a Grassmann odd operator, Grassmann odd which is invariant under LB. Then what you have is that actually the deformed partition function that we have defined this way, it is invariant by, it's not dependent on T. So it means that you can compute the partition function at whatever value of T that you like. So let me just explain you why this is useful. And that is the case because indeed Z over dt and we also use the fact that the measure is invariant, so this symmetry is, if you want to say it, not anomalous. So your partition function, so we have used the fact that we had like that V was invariant under LB in order to rewrite everything in terms of a total derivative. So indeed, given the fact that the variation of the four partition function is really 0, so this thing can be computed both at t equals 0. So t equals 0 means that you have the original partition function, but can also be computed at t. If you want to be extravagant, we can use it to compute it at t equals infinity. And so if you compute it at t equals infinity, and if delta v, so if you compute at t equals infinity, and delta v has positive definite bosonic part, then this thing, like then the entire path integral localizes on the the integral on the locus in which delta v equals 0. And this is in general finite dimensional. So in general, you will be able to compute Z, in our case will be the supersymmetry partition function for t goes to infinity, and this will give that it will be a sum over, in general, like for localization, in general you have a finite number of saddle points, and this you reduce it to like saddle point approximation into classical action and the one loop determinant for fermions, determinant of bosons. Also, many of the contributions from these two kind of operators will also cancel each other, so there are tricks in order to compute this kind of thing, in such a way that you don't need to compute the full determinant, but you compute just a part of it, just the parts that do not allow for cancellation between these two. So in general, this is the general principle of localization, and that's why people, and they use indeed supersymmetry, because supersymmetry is indeed of this form. It also like squares on Lorentz transformation. And so this is in general the principle that you have, that you use in order to localize your partition function. So I'm not going to go through the computation of the partition function via localization, but I'm giving you only the result. So in general, when you compute all these partition functions, you also need to choose a particular rigid background in which you compute the BGM partition function of, because indeed you compute this partition function at the boundary, and the boundary should match really the black hole, like the black hole geometry, the boundary of the black hole geometry. So in this case, our black hole, like the boundary of a black hole, is of the form S1 times sigma g, right? So this is the Euclidean boundary of the black hole geometry. And indeed, one can compute the BGM partition function on this boundary with also 1 unit of magnetic flux. On sigma g. And one indeed, like if you indeed like work out this partition function, so there would be Z EBGM on S1 times sigma g equal in the large n limit so it will be g minus 1, the partition function on S3, and this is exactly equal to g minus 1 pi over 2gn. So this indeed coincides with, let's say, this is S black hole, which is equal to minus I on shell action, for this very simple configuration. So here, I just stated the results. Unfortunately, I didn't want to go through the entire computation of this thing, but just the general procedure is that you put a BGM on a rigid background manifold. This rigid background manifold is the boundary, is the Euclidean boundary of the black hole that you're interested in. So in that case, the Euclidean boundary is just the time, but we compactify it. We compactify it on a circle, this is Euclidean time, and then sigma g is just the surface, which is in the surface of the horizon. So in general, this corresponds, and this also coincides with the black hole entropy of the black hole that I was showing you before, the minimal black hole, but it also, with a bit of work, people computed the partition functions with additional fluxes. So they use a more involved, like supersymmetric background, which allow also for flavor symmetries. In particular, the flavor symmetries will turn out to be related to the further charges that this solution with scalar has. So in general, in a BGM, then you can also, for the rigid, let's say for the rigid, so the vector multiplets responsible for the flavor symmetry are denoted with this, a mu flavor, and there are fermions that we don't care about it here, but also there will be some scalar fields. So these are the background vector multiplets. And these will appear, these fields which are related to the background vector multiplets will appear in the covariant derivatives, for instance, of BGM, plus it will also generate mass terms. So mass deformations. So also in this case, we need to impose the constraint. To match your bulk theory. So basically, you impose this constraint between the value of the magnetic fluxes for your background vector multiplets in such a way that you match exactly the quantization condition that you have in the supergravity black hole solution. Also, this is also known, like it's also required by the fact that your background will preserve some supersymmetry, or it should be. Also, by turning on these further couplings, one gets exactly a partition function which can be directly related to the solution that we have here. And the result for the partition function is this. So I'm going to show you here the partition function on the sphere. So S1 times S2, just for simplicity. So I'm going to just also drop some of the proportionality factors here, but it's basically... And I'm going to define all the things just in a moment. And we also have set k equals 0. Sorry, k equals 1. This is the Chern-Simon level. And this is like, yeah, if you want, it's proportional to n to the 3/2. So I'm dropping some of the numerical factors around. So I think just put it like this. So basically, what you get from localization So we put a BGM on a background. Rigid background whose geometry, like fixed geometry, is S1 times sigma g, or in this case, S1 times S2, so specified to this. Then we couple a BGM to further non-dynamical multiplets, which are so-called background multiplets. In particular, there are vector multiplets, which have a gauge field inside, this A mu f, which is like responsible for the flavor symmetry, and also some other scalars, for instance. And in total, the BGM, once you compute the partition function via localization and you expand it at large n, the leading value that you get is a function which has this particular dependence on n to the 3/2, which we'll see exactly is suitable for reproducing the black hole entropy. Moreover, the partition function really depends on the values of these background fields that were there in our background geometry. So in particular, depends on these deltas that we call also the fugacities. So it will be clear in a moment why we call the fugacities, and on these background fluxes for the magnetic charges. There is a constraint also, that is this one. So in order for your supersymmetric background to preserve some supersymmetry, all these fields here, they need to sum to 2 pi. 5 minutes? Okay. Then I think, okay, okay, so I'm gonna leave the formula here, let's say, on this side. And I'm gonna just go back to the supergravity equation that I was mentioning before. So we have seen, well, okay, maybe I'm gonna just explain, instead of going on with the supergravity, I'm gonna explain a bit more how this formula is derived. So this formula also has a meaning in terms of the, let's say, superconformal quantum mechanics that we find at the horizon. Let me just... So the partition function, supersymmetry partition function on that sort of like, or even the one that we found before, has a meaning in terms of the superconformal quantum mechanics that we have at the horizon. So our theory starts from ADS4 and then ends up in an ADS2 times sigma g geometry. So this ADS2, like that's conformal symmetry, so it is dual to a superconformal quantum mechanics. And the partition function that we have here can be equivalently seen as a Witten index for these supersymmetric quantum mechanics, in particular of this form. I don't know if you're familiar with the Witten index, but I'm going to explain you a bit. So basically, the theory that you get from reducing a BGM on S2, even in the presence of magnetic fluxes, the partition function that you have here can also be seen as the partition function in the quantum mechanics. However, it's the fact that it's a supersymmetric partition function materializes in the fact that you have like a trace, let's say trace -1 to the f. So there is a weighted trace because fermionic and bosonic degrees of freedom are weighted in a different way. Fermionic with a minus sign and the other one with a plus sign. So you've seen that here only the states, so I don't know if you're familiar, well, supersymmetry, I mean, I give you a lightning review, but basically for supersymmetry you have that states with non-zero Hamiltonian or non-zero momentum are characterized by pairing between bosonic and fermionic degrees of freedom. So whenever your H is non-zero, there are cancellation between bosons and fermions. So this index here is 0. So this index counts only states with H equals 0. So counts only the ground states of your theory, supersymmetric ground states, and also it's independent of this parameter that I call beta. That's also why we can compute our let's say our partition function on S1 of circle beta, because then actually the partition function that you get is independent on beta because it counts only states with H equals 0. Moreover, these are the flavor symmetries that commute with the supercharge. So this is only also written by this. So it means that your states in the partition function are also weighted with this further weight, which is proportional indeed to the value of the fugacities for the flavor symmetries. So basically, this is like the equivalent between this and this tells you that the partition function, which can also be equivalently seen as this Witten index, counts only the ground states of your theory, which also preserves supersymmetry. So it should be able to reproduce the black hole entropy. So we have seen it already in the case where we have a black hole without scalars. This was a very short computation, but we're going to see that when you have scalars, the matching between black hole entropy and the localization formula will show some interesting interplay between extremization principle, such as, for instance, the extractor mechanism in supergravity and the mechanism of CI extremization in the field theory. So having the formula that allow for a matching for the entropy for a black hole with scalars is really tells us a bit more with respect to what we get only from the undeformed theory without any any background vector multiplets. So I think that we can maybe stop here, and then if you have, and then
Can resume in 5
yes, yes.
minutes.